got these three people pushing boxes of the same mass at slightly different directions. Well, we said that force of friction is a relationship between, or the coefficient of friction ends up being a relationship between the force of friction and the normal force, yes? Okay. So we're going to talk here about kinetic friction. We're going to pretend we've already gotten these boxes moving. We're going to talk about kinetic friction. So mu sub k. And mu sub k is equal to the force of kinetic friction over the normal force. Right? Okay, good, good, good. So let's look carefully at each of these scenarios. I'm going to switch marker colors. I want us to think for a minute about the other forces that are in play here. So on each of these boxes, what other forces do we have?
Gravity.
Pardon?
Gravity.
Gravity. Okay. On each of these, we have a force of gravity, and I should make these about the same. They're the same mass.
Is that a Wicked reference that you just made?
No?
Okay, now I just sounded like
It's a Beatles reference. Gravity.
Okay.
It's this thing pulling me down, you see. I am attracted to the earth. I forget the rest of it. Okay, so F sub G, F sub G, F sub G.
I'm going to turn that into a record label from this video.
F sub G?
No, the singing.
Oh, okay.
Yeah.
All right. Oh, God, that's going on YouTube. Okay. All right, what other force do we have here? Normal force. Our friend normal force.
Normafer. I just felt like saying that. I don't even know why I said it.
Okay. So, let's do a quick little sum of forces thing here. I want specifically to look at what effect this pushing, this application of force to the box is going to have on normal force. Can the force that you're applying to an object change the normal force? Yeah, it sure can. So in this case, because the little tiny person is applying their force on both, so this is force of the person on the x, force of the person on the y. Here, is this person applying any force on the y-axis? No. It's all on the x. Here, our big giant person, are they applying any force on the x and the y? Yeah. So we have force of person on the x, force of person on the y. All right. Let me get this out of the way for now. We're going to assume that the coefficient of static friction between this surface and this box is, we'll keep the math easy, 10.0. 10.0. We're just going to talk about that in a second. Okay.
Whoa. What is that letter?
What?
Mu sub.
Mu k.
Oh, okay.
It's bad handwriting.
Mu k.
Mu k. All right. So in this case, let's do a sum of forces. We're kind of going to disregard the x-axis for right now because we know this thing's going to move. That's fine. Or we assume it's going to move. I guess I shouldn't say we know it. All right. So here, sum of forces on the y-axis. Well, what we got? We have F sub n. Let me ask you this. Is the force of the person on the y, is it going to be adding to the normal force or subtracting from it? Adding. It's in the same direction as normal force. So plus F sub py. Force of gravity, of course, is in opposition. All right. Here, does their applied force have anything to do with the y-axis? No. All right. So let's go over here. Sum of forces on the y. Well, we've got F sub n again. Is the applied force adding to or subtracting from the normal force? subtracting. It's in opposition to the normal force. Okay. So, we assume, we've not been told that any of these boxes are rising up into the air or sinking down into the ground, right? So we're going to assume that the sum of forces on the y is 0. So now, solve for normal force. So here's the thing to be aware of. In this case, where the applied force is upward, is the normal force going to be greater or less than the force of gravity?
Greater. Less.
Less. It's going to be less than the force of gravity because this applied force is actually kind of lifting the object. In this case, is the normal force going to be greater or lesser than gravity?
Less.
Less. Good. Wait!
Yeah, it's a joke.
Oh, okay. I haven't finished my second cup of coffee. No jokes. Yeah, it's going to be greater than the force of gravity here because the applied force is actually pushing this object down into the surface. Yeah, because it's added here. See that? Huh? It has to be greater. No, we're just on the y-axis right now. All right. So, in this case, what's the relationship between normal force and gravity? They're equal. Yeah. There's no other force acting on the y-axis. As long as this thing is not rising into the air or sinking through the surface, gravity and normal force are equal. And this is on a flat surface, not a slope. All right. Now, why are we talking about all of this in the context of friction? Does this change the force of friction? Oh, it most certainly does.
And if you're pushing down on something, it's going to give it.
It's a whole lot harder to move. You know that conceptually. You get that conceptually. But now our job is to look at it mathematically. So, if we recall, we said that mu k equals force of kinetic friction divided by the normal force. So if you solve for the force of kinetic friction, you have mu k times normal force equals the force of kinetic friction. Because that's the one force we did not label here. Ooh, I have a new blue marker. Fantastic. So we'll do a force of kinetic friction going back that way. Okay, so in each of these cases, let's do some quick math and solve for the force of kinetic friction. All right, what's the force of gravity in each of these cases? Equal to mg, so equal to 10 kg times 9.81. So F, oh, that probably can't be seen. F sub g in all cases is going to be 98.1 newtons, right? It said haven't finished the second cup of coffee. Yeah, okay. 98.1 newtons. In this case, and let's say that all of these people are capable, so in each case, the force of the person is, we'll make that 150 newtons. Okay. Well, what's the force of the person on the y? So here we've got our 98.1 newtons minus 150 newtons times sine of 45. Okay, so we have an applied force on the y of 106.066, etc. newtons. So 98.1 minus our 106. We actually have a negative normal force. Oh, crud, I lost the computation.
Wouldn't gravity have been negative, and then you would have added normal force instead of subtracting it?
Well, but remember in these we tend to use mg and we don't use the negative on gravity.
Alright.
So, and this is in opposition to gravity. Yeah. You know what? I'm going to have to think about this again, aren't I? Okay. Let's stick with conceptually for the moment.
Oh, nice.
Come back to that.
These are going to get really hard, aren't they?
Huh?
These are going to get really hard,
They're
aren't
going to get interesting. They're going to get interesting. So conceptually, you know that it's going to be easier to push this object. The force of kinetic friction is going to be reduced here and increased here because of the force being applied, either opposing gravity and therefore adding to normal force, or the force applied adding to gravity and opposing normal force. Okay? We'll shut this off. I'm going to pass out the 4C and 4D packet.